Hi there. In this video, we're going to talk about the radial equations that we derived previously and talk about the free particle solutions to them. So before I go into the solutions, let me just kind of remind you what the equations are and also just talk about the angular momentum operator first. So in quantum physics, we have defined a momentum operator, right? P equals IH bar, actually negative IH bar, sorry, it should be positive. IH bar times the gradient function. You can also have other observable operators like angular momentum, right? Energy. What you usually do is you basically plug in the momentum operator anywhere the momentum appears in the classical physics equation. So I can do that for angular momentum. Angular momentum is R cross P, RP sine theta. Hopefully you've seen a cross product before, but basically it's mainly R times the momentum. There has to be some rotation though, which is where the cross product comes in. Either way, we can get this angular momentum operator that we saw when we wrote down the kinetic energy term in the Schrodinger equation. And just to recall, this angular momentum operator squared, if I try to solve the eigenvalue equation for it, I get spherical harmonic functions that solve that eigenvalue equation. Basically what they do is if the operator operates on that function, it returns a constant value, which turn out to be the actual observable values of angular momentum. And they depend on this quantum number L equals 0, 1, and 2. And as it turns out, there's another quantum number here, M, which doesn't affect the energy in a spherically symmetric potential. But it does affect it if you apply, for example, a magnetic field, something like that, to the atom. But you get this M number, and if you take the Z component of your angular momentum and operate on that spherical harmonic, you get another eigenvalue type equation. It kind of pulls out a constant times the spherical harmonic. And M could be negative L plus 1, 0. So it ranges between negative L and L in integer steps, right? So if L is 1, it goes from negative 1, 0, or positive 1. So if you've ever studied chemistry at all, you see the electron shells around the atom. You've got your L quantum number, which describes the angular momentum. And then you've got this M quantum number. Turns out there's another quantum number associated with the spin of the electron. But maybe we can talk about that in the future. I just wanted to bring this up because you sometimes see it in books when they define the spherical harmonics. They go into great detail on these angular momentum operators. Right? And maybe we could do that in the future. It's a very interesting but somewhat complex subject. So back to our matter at hand, we want to look at the radial equations for the radial functions UL that we derived previously. Now remember, a general wave function can be written as a sum of these radial functions as coefficients of the spherical harmonics. So I've got sort of a product of radial functions and angular functions, the spherical harmonics. So what I'd just like to do now, and actually I wrote it down here, what I'd like to do now is look at how do we start to solve for these radial functions? And how do we start to tell what they're gonna mean as far as an experiment goes? In this lecture, I'm not going to get that far. What I just want to look at is the case of a free particle. And by that, I mean there's no potential energy here, right? The potential energy is 0, which means there's no force. Now, that could not happen for a real atom necessarily because you've got electrons and protons and there are Coulomb forces. But generally speaking, right, an atom has the same number of electrons as protons. And so if you're far away, this potential tends to go to 0. You're kind of just got a neutral target. When you get close, then things can happen. The potential may not be zero. So let's go ahead and assume, though, that our potential is zero, and just set that potential term to zero, and we get this equation. The first case, now actually, I guess you could say there's actually sort of a potential here. There's a centrifugal term. This is, again, due to angular momentum, right? And if you think about it, an object that goes in some kind of circle around a point has angular momentum, and there's sort of a centrifugal force due to its rotation that tends to throw it out. It tends to be kind of a repulsive type of force there. And now let me think, yeah, I think this should be, might want to double check the sign there, whether it's positive or negative. But either way, I get my radial equation, and let's look at the S wave case when L is equal to 0. So when L is equal to 0, basically, we just have d squared, dr squared plus k squared. This is just like a simple harmonic mass on a spring type of equation. The solutions when L is 0 are just sines and cosines. So generally, I could write out the solution as a sine of kr plus b cosine of kr. Another way to write this is a e to the ikr plus b e to the minus ikr, right? Where a and b may be different constants. And recalling that sine and cosine is related to the exponential e to the I theta function by cosine of theta plus I sine of theta is equal to e to the I theta. This is called Euler's formula. So you can switch back and forth between sines and cosines using that formula if you want. But basically, they both describe the solution when L is 0, and you could actually plug these in and show that you do get 0 when you do that. Now, the problem is, of course, you need to understand what these constants are or be able to determine them. We are going to talk about that here, maybe not completely today, but in the next video. Typically, again, what happens is that the potential goes to 0 as R gets bigger. And so you get far away from the atom that you're scattering from, right? And this U is describing the scattered electron, for example. It reaches the asymptotic region where the potential is 0. So we often look at these as asymptotic solutions. The solution that you actually get for a real problem like this should turn into this type of solution far away. Now again, I'm right now just looking at the case for L equals 0, and this is sometimes called the S wave. L equals 1 is the P wave, L equals 2 is the D wave, and so on. But we're going to keep it L equals 0 for now, and then we'll just generalize the solution. Now there are other ways to write, or that are common that people write this solution as. Another way is that you could introduce a phase here. Now, again, I'm looking at this as an asymptotic solution, right? So basically, when we interpret the result, what we will look at is this phase shift. If you have a solution that's far away, it might be changed when you add in the potential, and it will lead to a phase shift in your solution. So we call this delta 0 the S wave phase shift. Ultimately, as it turns out, in scattering problems from spherical potentials, right, that are spherically symmetric, our main goal is to determine the phase shift. It is related to the scattering cross-section. But again, in the next video, I will have to show you what that relation or how that relation is. Let's just rewrite this solution in a few different ways. One way to do it is to use a trig identity, right? Sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. And I'm just going to apply that to this. So I get a sine kr cosine delta 0 plus a cosine kr sine delta 0. Now I'm going to pull out this a cosine delta 0 And then I'm left in parentheses with a sine plus tangent delta 0 times cosine kr. Now, this a is an unknown constant, right? I could define a cosine delta 0 as a new constant, and I could even set it to 1. Turns out when you have free solutions that can exist at r equals infinity, they are not quantized. And in fact, you could not integrate this solution to normalize it, right? You could not normalize a solution that does not go to 0 at infinity. So the way that we interpret the coefficient here, the square of the wave function, is again like we did for the one-dimensional barrier problem. It's a relative probability. We're going to think of an incoming wave that hits the atom and then it somehow reflects and we get an outgoing wave. The ratio of the square of the wave function incoming to the square of the outgoing wave is in some way related to the experimental probabilities or cross-section we can measure. Now maybe that doesn't make a lot of sense right now, but I want to kind of start to get us to realize how the math here is connected to the experiment. But for now, this is just another way of writing the asymptotic solution. Now, a lot of times people will call this K, this tangent delta 0, K0. It's related to the reactance or K matrix. Maybe we'll talk about the matrix more later, but this is just another way of writing this. And it turns out, right, you can write for other partial waves, other values of L, you'll have a KL equals tangent delta L. Another way to write this, I should write U0 here because I'm still just talking about the S wave, L equals 0, although again it generalizes as we'll see. So when I write this way, right, in terms of e to the IKR and S and e to the negative IKR, I can do a little bit of algebra and I can find out that the coefficient that multiplies e to the negative IKR is given by this formula. It's related to the K matrix by this relationship. And this is often called the S matrix or the scattering matrix element, right? We don't have the whole matrix yet. We just have the L equals 0 S wave element of it. But it's related to the phase shift by e to the 2i delta 0. So again, two different ways of writing the asymptotic solution. They are both related to the phase shift. So the phase shift is kind of the basic fundamental thing. Let's write it one more way for another, because there is another quantity that's often used when you talk about quantum scattering. I could write it as u sub L. I could change my e to the IKR to a sign. Turns out there are always some constants that come in. I'm going to multiply by 2i here so that I get a t in front of my e to the negative kr. And you can show that T0 is 1 minus S0. This is often called the T matrix. So all three of these ways are just different related methods of writing the asymptotic solution. Okay, phase shift though again is in all of these, and the scattering phase shift is what we often end up solving for. Okay, so hopefully that makes some sense. Maybe it makes more sense as we actually do problems. But let's look at the case for a general L that's greater than 0. We can define functions that are solutions to the radial equation for other values of L. Okay. Now it turns out that these are known functions, but we can always write our SL function plus KLCL, and we have a kind of a generalized K matrix. And we have other phase shifts for different values of L. So you'll have an S wave phase shift, a P wave, a D wave, right? L equals 0, 1, 2, all these different phase shifts. As it turns out, if you want to get the fundamental solutions that are related to sines and cosines for L equals 0, you get functions that are called Riccati-Bessel functions. And they can be written in terms of what are called spherical Bessel functions. Lots of different types of Bessel functions. Now the spherical Bessel functions, I'm just going to write down the L equals 0 form. Turns out it's J0 is defined as the spherical Bessel function that goes to a constant value when r is equal to 0, and it's sine of kr over kr. Now n0 of kr is sometimes called the Neumann function, spherical Neumann function. And lots of different names, and there are other Bessel functions that these spherical Bessel functions are related to, but you can look them up. Even on Wikipedia, they have a list of the first few spherical Bessel functions. But n0 is negative cosine kr over kr. Now to get the Riccati Bessel function, all you do is take kr times your spherical functions, or times your J0, or negative kr times your n0. These are the solutions to the case when the potential is 0 for any value of L, right? If I use the particular JL or NL, right? So in general, the Lth Riccati Bessel function that has sort of a sine behavior is SL. The one that has sort of a cosine behavior is CL. Now, if you go to really, really, really large R, eventually that potential is just 0, and you can make sort of an asymptotic expansion of these functions. And what you find is that the Riccati Bessel function SL becomes a sine function, right? It's kind of like you're out almost in the case where the L term is very tiny, right? The R is very big. But there's sort of a phase shift due to that L times L plus 1 over R squared term in the radial equation. So you get a sine behavior. For the CL function, as R goes to infinity, you get a cosine behavior. So again, as R becomes really huge, you can use these. But you can't use these forms at small values of R. Okay, so last thing here for right now. How do you find the KL or the delta L, right, the phase shift? Typically what you have to do is do some kind of matching. And often we will split the region around the atom into sort of two places. You've got a sphere that surrounds the atom, and I'm going to call that region 1, where the potential energy is not equal to 0. This is where the electron is really interacting with the atom. When it's in that radius, R within Rm, you got to solve the whole equation, and often you have to do that numerically. But what you can get is the solution UL1 out here at this matching radius Rm. Okay. Then outside in region 2, if the potential is 0, we know the solution, right? It's written in terms of, let me go up here, it's written in this, SL plus KL CL. How do I determine KL? Okay, well, what I do is I do a matching of the derivative. Turns out the derivative has to be continuous across this change in potential. So does the function, right? The function can't just change values all of a sudden. It's got to be continuous. So I have to match the value of the function in region 1 to region 2 at Rm, and also the derivative. Now, a quicker way to do this is to take what's called the logarithmic derivative, which is just the derivative divided by the function. So I take the derivative of my region 1 solution, evaluate it at the radius, divide it by the solution itself at the radius, do the same for the region 2 function, divide it by its solution, and just set them equal. This gives me an equation for K. I can solve that for K and then determine the phase shift, and ultimately we will be able to determine the scattering cross section, which can be related to a measurement, right, that is done in the lab. So a lot of math there. Other things I should maybe point out, oftentimes you have potentials that don't really go to 0 very fast. You have to integrate out very far before the function, before the potential is small enough that you can do this matching. Some cases, like the Coulomb potential, never really get that small. And it turns out you have to write your solution in terms of different asymptotic functions when you have a Coulomb type of problem, like maybe an electron scattering from a proton, right? Well, then there's a Coulomb force that exists. All right, so hopefully that makes some sense. In the next video, what I hope to do is show how my scattering cross section that you measure experimentally is related to this phase shift or the KL or the SL or the TL, right? The scattering matrix or the T matrix. A lot of this stuff is contained, I believe, in Griffith's book, but it's not till the very later chapters, maybe chapter 13. So if you wanted to try to look at that there, you could. I've skipped over some of the math just to hopefully get to some of the basic points, right? Again, that we have an asymptotic solution and that we match, where the potential is 0, and we match that to the solution we actually numerically solve in our region 1 here. Okay, I'm going to stop there because this is getting kind of long, but I'll try to do another video involving the cross section next.